Welcome back to Honors Calculus. In this video, I'm going to be talking about area. And for simple shapes, I am certain that you have calculated the area of these figures many times in your mathematical careers. For example, if I draw a fairly straightforward triangle, maybe I draw a triangle. There we go. That's actually a terrible triangle, but we can do some quick triangle surgery on it and get a very nice looking triangle out of that. All right, if we draw this simple triangle, and I'm going to go ahead and say that each of these grid marks on my page is 1 centimeter in size. Depending on the size of your screen, that might be very different. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 centimeters looks like the distance that way. And hopefully you know that if I measure perpendicularly from that side up to the highest peak, which I happen to have made sure fell nicely on the corner of the square, 1, 2, 3, 4, 5, 6 squares going up, that we can calculate the area of this triangle is 1/2 times the length of its base times its height. In this particular case, the length of the base is 11, the height is 6. 1/2 times 11 times 6 is 33 square centimeters. Right? Nothing new there. That's old hat. That's something that you should be able to do in your sleep at this point. And so that's not what I care about. What I care about is what if we have a really ugly looking figure? What if I have this potato looking shape and I want to calculate the area of this shape? Well, I don't have a tool for finding the exact area. So instead of the exact area, I'm looking for the approximate area. And I can use the grid on the screen behind me to my advantage again, right? If I said that each of these squares measures 1 centimeter across, then the area of one of these squares is 1 square centimeter. One way I can approximate area is looking at how many of these squares are inside of the shape. Now that gets to be a little bit tricky because I've got a lot of these bits of the shape where some of the square is inside and some of the square is outside. If you've seen something like this in the past, you probably were taught to give a judgment call. Count the ones that are more than half inside the shape as in the shape, count the ones that are not as not inside the shape. I want to do things a little bit more formally here. So in fact, if I get my head out of the way, I'm going to take advantage of the fact that I have a digital touchscreen. I am going to copy that shape that I just drew, and I'm going to paste it over here, lining up my grid as nicely as I can to what I had before. It won't be perfect, but it'll be pretty close. Obviously, if you are trying to do things pencil and paper, that's going to be very difficult for you. If you don't have graph paper, that's going to be very difficult for you. And even if you do, your shape is going to be different than mine. The actual numbers here don't matter. But what I want to do is I want to calculate what we're going to call, let's get this question out of the way. I'm going to calculate a thing called the lower sum, and then I'm going to calculate a thing called the upper sum. For the lower sum, I am going to count only the squares that fall entirely inside of this shape. If there is even the slightest bit of the shape that falls, or of the square that falls outside of the shape, I am not going to include it. Obviously, this is going to underestimate the shape. In fact, that square that I just cut out is so incredibly close to being inside the shape, but it doesn't quite make it, so it doesn't get included. And so I get something that looks kind of like this. And if I fill in and I get all of these shapes, I mean, I don't necessarily need to highlight all of them, but depending on your screen, this might help you see where my grid is a little bit better. And it doesn't take that much doing. And so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 1, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43. The lower sum gives me 43 square centimeters. On the upper sum, I'm going to be on the other extreme. I'm going to count the squares that have even the tiniest sliver of area inside of the shape. And so I'll count this square that just has that tiniest corner inside. And I am definitely overestimating the area here because I am counting these really, really tiny regions. But that's okay. I know that I am overestimating, and I am intentionally overestimating in this particular case. Right? My overestimate gets me all of these squares, right? All of the squares that contain even the tiniest sliver of the shape. And clearly everything that was in my lower sum is still here, but I've got so much more. If it helps, we can draw in all of these grid lines. Again, depending on your brightness, the brightness of your screen, you may not be able to see those as clearly as I can, but they are all here. All right, let's do a little bit of a celdectomy here to get rid of that bit that I drew very poorly. And once again, we can count all of these cells. Each one is 1 square centimeter. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Put a big dot there so I can make sure I know where I am if I lose my place. 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 2, 3, 4, 5, 6, 7, 8, 9, 70, 71, 2, 3, 4, 5, 6, 7, 8, 9, 80, 81, 82, 83, 84, 85. My upper sum comes to 85 square centimeters. And so the area of this shape is somewhere between 43 and 85 square centimeters. And again, if you had taken that advice that I gave when I set out to do this, if we just look and take the ones that seem close, count the ones where most of the cell is in, and exclude the ones where most of the square is outside of the region, we would get a much better approximation than somewhere between 43 and 85. And yes, that's absolutely correct. But this is calculus. And so we have a tool that we can still use, because we could get a better approximation if we had time and we had precision. Why did I superimpose this figure on a grid where each cell was 1 square centimeter? Why didn't I choose a grid where each cell was 1 square millimeter, a tenth of a square centimeter, or actually a 100th of a square centimeter? If I did that, I would get better precision. My lower sum would include more of the spaces that got cut out. My upper sum would include less of the spaces that seem egregious. And then I could divide things further. And I could divide things further. And what if I just kept dividing this into smaller and smaller regions so that my lower sum got bigger and bigger and bigger, and my upper sum got smaller and smaller and smaller? Eventually, they would meet in the middle. In the middle is the area of the figure that I'm looking for. This is the squeeze theorem that we talked about when we introduced the idea of limits back in the beginning of the course. All right, so let's let n be the number of divisions to draw in, the number of squares that I'm drawing on my page before I start counting which ones are inside and which ones are outside. And I'm going to take the limit as that n goes to infinity on the lower sum and on the upper sum. If those two sums converge and they converge to the same value, by the squeeze theorem, that limit has to be the area of the shape that we're looking for. That is the approach that we're going to use. That is the tool that we want to take into consideration as we try to figure out a rule for dealing with area. Now, taking a completely arbitrary shape is still going to be a challenge, although we're going to get a lot closer to being able to do something with it by the end of this lesson. For right now, we're going to be looking at shapes defined by functions. Specifically, we're going to be calculating the area under a curve. If I set up my x and y coordinate axes, for simplicity, I'm going to always draw this in the first quadrant. We'll see later on how we can extend this. But then I get some curve here, y equals f of x, and I get some points in question. The area under the curve y equals f of x from x equals a to x equals b is going to be denoted using this funny S-looking symbol. We read this as the integral of f from x equals a to x equals b. The notation here seems a little bit backwards in time. And so it's worth taking some time to think about what's going on here. This dx, we've talked about differentials in the past. That is the differential of x. And it will make more sense as we go through and set up a way of dealing with this. But for right now, this differential with x is telling us that we want x equals our lower limit and our upper limit, a and b. So f of x dx, we just call that function f. We're lazy, we don't have to say everything. And the fact that it's dx tells me that we want x equals a and x equals b as a nice way of thinking about that. And so we're going to figure this out using a tool called the Riemann sum. We want to divide up the interval from a to b on the x-axis here into n subintervals. Now, dividing a line is not a mathematical operation. The mathematical operation is called partition. Our goal is to create intervals so that there are n of them. They do not overlap, and they cover the entire interval. So we're going to look at cutting this interval up into pieces. I've drawn it here with 6. But it doesn't really matter how many you use. For each of the endpoints of this, I'm going to draw a vertical line that comes up and touches the function. And I'm going to use that vertical line to draw a rectangle. And if you're paying close attention to what happened here, I'm basically doing what we just did with the arbitrary shape. I'm drawing this area. I am measuring a bunch of rectangles, and I'm trying to figure out how they relate to the area. I've drawn this curve so that these rectangles are actually pretty good, but in some spaces, they are underestimating. All right, there's a little bit there of area under the curve that's not getting counted. In other places, they're overestimating. There's a little bit of area here that is in the rectangle that's not under the curve. If we took more regions, we would get a better approximation. We could choose, instead of drawing the rectangles on the right, we could have drawn the rectangles on the left. That is our upper sum and our lower sum analogy that we talked about before. The important thing is that they should converge, and they should converge to the same point. And that point that they converge to as we take the limit is going to be the area we care about. All right, so call one of these points that we've just created xk. We're going to introduce a parameter delta x, which is b minus a over n. Right? The length of the interval divided by the number of subintervals, and that's going to give me the length of any one of these divisions. I'm going to set up xk equals a plus k delta x. And note that x, getting ahead of myself, x0 is a, and xn is b. Right? X0 is a is very obvious. Xn is b is a little bit less obvious. But if you substitute in the definition we just came for in delta x, you'll see that you have n and you have divided by n, which cancel each other out. And then you'll end up with a and minus a, which cancel each other out, and you're left with b. So this formula is telling us in the picture 0, 1, 2, 3, 4, 5, 6. How many of these steps we want to move over is xk. Then we can figure out the height of the rectangle. Actually, let me stay up here and talk about it, and then I'll go back down and draw it out. Right? At xk, the height of this rectangle is our function evaluated at xk. Right? This region is between x0 and x1, and the height was determined on the right-hand side by x1. So the height is f of xk. The width I already said was delta x, but let's go back and look at that picture one more time. right? The height is determined on the right-hand side. The width, the distance between one of these, we took the entire distance across and we divided it by the number of pieces, and that gave us the distance of each one of these. And if you multiply that width times that height, you get an area. So the area of the kth rectangle that we've drawn is f of xk times delta x. And the total area is the sum. K goes from 1 to n of f of xk delta x and again, remember that's the approximate area that our drawing has given us, and the actual area is the limit as we take more of these. The more of these rectangles we get, the bigger this thing is. And the more intervals we get, because delta x is the width of the interval divided by n, that delta x at the end becomes infinitesimal. And that's why delta x as n goes to infinity becomes the infinitesimally small differential dx. By the time we've gotten to this form, we are looking at every instantaneous spot going across the x-axis. We are multiplying the width of that infinitesimally small spot times the value of the function, which is the height of the rectangle that is infinitesimally small, to calculate the area of that tiny sliver. And we're doing that step by step by step. And that's why the differential makes sense to appear here. So as we take these regions and we get them narrower and narrower, we get something that we can actually work with. So for example, I might want to approximate the integral from 1 to 2 of x squared dx for n is equal to 4. If I draw this, and I'm going to draw it quite a bit larger than you usually would draw something like this. We know that the parabola looks something kind of like that. We can subdivide the interval from 1 to 2 into a couple of smaller regions. Calculate that our delta x is 1/4. And we can evaluate f of 1 plus 1/4 is, well, 1 plus 1/4 is 5/4. And 5/4 squared is 25/16. Then we'll take 2 times 1/4, which is 1/2. 1 plus 1/2 is 3/2. 3/2 squared is 9/4. All right, 3 times 1/4 is 3/4. 1 plus 3/4 is 7/4. 7/4 squared is 49 over 16. And then 4 times 1/4 is just 2. 2 squared is 4. All right, so that's telling us we want to draw our rectangles looking something like this. And yes, we can see from the picture that we are going to pretty drastically overestimate the area, but it will give us an approximation, and that's sometimes good enough. All right, so in this case, f of xk when k is 1 is 25 over 16. And then we have 9/4. We have 49 over 16. And we have 4. All right, so that's 25 over 64 plus 9 over 16. 49 over 64 and 1. Find a common denominator of 64. So that'll be 36 over 64, multiplying top and bottom by 4. "25 and 36 is 61. 61 and 49 is 110, plus 64 is 174. And those are both even, so I can divide by 2. Getting that the area in this case, or the integral in this case, is approximately 87 over 32. All right. So that's the big idea of area and approximations of area. I want to keep playing around with this, so I would like you to try the calculation. This time, same integral, but with n equals 5 instead. See what you can do with that one. I'll see you in the next video.